My name is Daijia, and I'm a senior student majoring in biomedical engineering at San Jose State University.
So my name is Carlo. I'm a senior studying biomedical engineering at San Jose State University.
And our project topic is the in vitro degradation, study of the biodegradable PLGA Copolymers with different shapes. And our technical advisor is Dr. Selvaduray. And in this presentation, we will briefly talk about what our project is, why we conduct our project, how we set up the experiments, and what results and conclusion we obtain. Woods can be classified into the open woods and the surgical woods. Open woods are generally caused by the external and internal breaks, and that includes the abrasion, laceration, puncture, or avulsion. The surgical wound is intentionally caused by the surgeons or doctor during the surgery. The wound's healing process is fairly complex. That includes the hemostasis, inflammation, proliferation, and remodeling. Surgical sutures and the surgical stapler are two predominant techniques for wound closure. For the surgical sutures, the material we use can be the single PLA, single PGA, the nylon, the silk, or this surgical steel. Even though it can cause the minimal inflammatory response, it can cause a very long operation time and may bring patients the pain and the injury. The surgical staples can be made in the stainless steel or titanium. It is easy to use and in a short time. However, it requires the removal of the metal staples and can cause unsatisfactory cosmetic results and lead to the allergic reactions. So the absorbable skin stapler is our biomedical motivation. Such absorbable skin staples can provide a better cosmetic outcome, the rapid closure time, no need for staples removal, and lower indication of the infection. However, the rectangular skin staples shown in the figure is only available in the market for this medical device. However, many the customer reports indicate that the rectangular skin staples can cause the separation between the dermal surface, and it can tilt or pivotal perpendicular to the our human skin. This is because of the small interior angles, which can lead to the much loss of the holding strength after being implanted into human skin. And also the rectangular skin staples can have a comparatively longer degradation period, which is around 2 months. So the objective of our project is to investigate the relationship between the shapes of the staples and the degradation rate, determine the most efficient shape with the trade-off relationship between the degradation rate and the degree of stability, improve the ease of use, maximize the stability, and shorten the degradation rate after implantation. This can be achieved by increasing the length of the two legs, shortening the distance of the crown, and adding the central points. Those pictures shows our design skin staples with the C shape, U shape, and the M shape. This is the rectangular skin staples, which is available in the market. For the FDA consideration, we hope our design skin staples can be applied into the insole absorber staple, which is manufactured by the incisive surgical ink, and it is a Class 2 medical device. To manufacture or to make the skin staples, we use the PLGA as our raw material. This is because of the two important characteristics, the biodegradability and the biocompatibility. And especially the 50-50 PLA and PGA material has the fastest rate of degradation, which is around 2 months. And the PLGA material can experience the hydrolysis reaction to be degraded into the glycolic acid and lactic acid. There is a paper doing a comparison between two different skin staples. This is the original rectangular skin staples, and this is a modified skin states. The FEA experimental result shows that the modified skin states has a stronger culture strength after being applied into human skin. This is due to the larger interior angle and the wider distance between the two legs. And we also apply this important conclusion into our designing of the U-shape and the C-shape skin states. And another paper conducting a degradation test of the PLGA cube sample at the different temperature. And they explore the pH change, pH of the pH of the buffer, the media buffer, and the percent mass remaining change, and the percent molecular weight change as a function of time. And in our degradation test, we will test these three variables as well.
So in terms of the design of experiment, so in this project, we'll be investigating 4 different shapes, which is the M shape, U shape, C shape, and also the rectangular shape, in order to investigate the most efficient stable in terms of the stability as well as the degradation duration. So the entire project will be conducting in 37 degrees Celsius, which is the physiological temperature of the human body. So you can see in the bottom of the slide, it is the CAD file which shows the dimension of each stable of our design. So we try to maintain the constant areas as well as the volume. So we just only investigate how efficient it degrades. So for the next slide, so the material we'll be basically mainly using for our raw material as our skin stable is the 50 to 50 PLGA copolymer, which is a S terminate. So for the next slide, we can show the other material we use in this project, which is first we'll be using the acetone, ethyl alcohol, and also the PBS buffer solution to dissolve, precipitate the PLGA, as well as to act as a dissolution media in this project. So in terms of the equipment-wise, so the main equipment we'll be using is the laser cutting machine in order to manufacture the stable. So we'll be using an analog incubator as well as the thermocouple, which is a type T thermocouple, by connecting to the data logger to obtain a calibration curve and also to do the incubator calculation. So in terms of obtaining the main result, we'll be obtaining the weight, temperature, humidity, and also the pH of the project. So we will be using a mini scale, thermometer, as well as a humidity gauge, and also a pH meter. So the major method we'll be conducting will be consist of 5 major steps. I will be explaining one by one more detail in the following slides. So the first step we'll be using is the incubator calculation. So what we do is we'll be placing the 3 thermocouple, which is the type T as I mentioned before, in different position of the incubator in order to obtain the temperature variation inside the incubator by connecting to data logger and to have a calibration curve for us in this project. So in order to prepare the copolymer sheet, we are following the ASTM standard F1635-004A. So by what it means is we obtain the 20 grams of 50 to 50 PLGA and try to dissolve it into acetone to form an organic phase. So after forming an organic phase, we will be placing it into the steroid petri dish to form a copolymer by precipitating it using ethyl alcohol. So after we finish the copolymer sheet, we will be placing it into the incubator for a day in order to remove any water content we have during the preparation of the copolymer sheet progress. So the next step will be manufacturing the stable. So what we do is we will use the CAD file we have designed in the previous slide which I showed. So we will be uploading into the laser cutting machine in order to cut the same shape of stable using the laser cutting. So the main reason for using a laser cutter is we're trying to maintain the constant area as well as the volume to minimize the error during the dissolution test. So that's the main step we do is the dissolution test. So the whole project will be conducting in 37 degrees Celsius. So we are preparing 5 samples for each shape. So each shape will be weighted, and also the dimension will be measured for every 2 days of immersion in the PBS solution after for a day of desiccation to remove the water content. So the pH also will be obtained in this project too for analysis purposes. So at the end, we will be using the gel permeation chromatography, or also known as the GPC, to obtain the molecular weight measurement of our sample for one of the original PLGA sample, as well as all our 5 samples for each shape. So what we do is we will be dissolving into the THF organic solvent, and then place 1 millimeter of sample to the vial, and then put into the GPC machine to obtain the molecular weight.
Also, for the incubator calibration results, we found that the temperature inside the incubator kept constant with the time, and specifically the orange line shows the middle position of the incubator has a comparatively higher temperature than the left corner, and the right corner. So in the degradation test, we was trying to collect all the samples in the middle position of the incubator to ensure they can experience the same temperature over the time. And for the rectangular steps degradation test results, we found the percent mass remaining decrease with the time, and also the pH of the pH value of the buffer decrease with time from around 6.5 to finally around 3. And also the change of the pH can be used to demonstrate the mass loss. It's because the PLGA raw material was degraded into the 2 acidic products to cause a low pH value. And also, on average, the rectangular skin steps can be completely dissolved at the 6 to 65.2 days, and the initial fracture appeared at the 31.6 days, the light fracture at the 67.2 days, and the severe fracture at the 54.5 days. And for the C shape, the complete dissolution time is fairly shorter than the M shape, and we also can see the C shape steps have had a higher degradation rate than the rectangular shape. This is because we ensured all the samples have the same volume and using the same material to ensure a constant density of the skin steps. And also the initial fracture is around 21.6 days, which is also shorter than the rectangular skin steps. And for the U shape, the degradation time is shorter than the C shape, and the degradation and the dissolution rate is also higher than the rectangular shape. And for the M shape, it has the fastest degradation rate and the shortest dissolution time, which is around 32.8 days, and the initial fracture appears at the 20 days. So by combining all the data points, we found that the percent mass remaining as a function of time, and the yellow line shows the M shape was degraded first, and followed by the U shape, C shape, and the rectangular shape. So based on this table, in terms of the degradation duration, the overall degradation duration, and the dissolution rate, the M shape has the fastest degradation rate and the shortest degradation time, which is 32.8 days. However, in the terms of the degree of the stability, the rectangular shape has is the most stable among the other shapes. This is because the initial fracture appears at a longer time than the others. And obviously, there is a trade-off relationship between the degree of the stability and the complete dissolution time. And when we propose the most efficient skin steps shape, we need to consider those 2 factors, I think.
So in terms of the molecular weight, so based on our GPC result, it also confirmed that based on the parameter it obtained, so which is the Mn, which is the lumbar average molecular mass, the MW, the race average molecular weight, and also the D, the polydispersity index. So it's also confirmed that M shape will have the fastest loss of degradation rate, which also means that it will be having the fastest rate of degradation in terms of the M shape compared to the raw material we have. So for conclusion, based on the result we got, so the most efficient stable in terms of the degradation type we investigate is the M shape, followed by the U shape, C shape, and the rectangular shape. So in terms of the stability, the most efficient will be the rectangular shape. So we definitely find that there is a relationship between different shapes with the dissolution rate as well as the molecular rate of change. So since we believe that the stability and also the degradation rate will be a trade-off. So in order to investigate what it means by efficiency, in this project we try to focus more about the degradation rate. So we decided that the M shape will be the most efficient stable in terms of our project, the concentration is. So we believe that our result hopefully will be make some contribution to development on the wound culture as well as to act as a starting point for future researchers. So here's our cost in terms of the left side will be our equipment spend, which is around $1,800. So on the right side will be the $600 total is around the material we will be using. So for future work, we do admit that we have to consider like how the mechanism or how to apply the stable using the commercialized stable, which is the absorbable stable. And also we should also investigate the mechanical properties by determining the pre-operative and also the post-operative after applying on the wound. And also we also should consider how to quantitatively measure the stable factor instead of just qualitatively measure the stable by just using the observation. And also we should consider how the stability and reliability of the stable after applying on the wound, and then to consider what is the quality of the wound closure. And at the end, we should also maximize the stability of the stable, applicability, and also the degradation duration. So we want to thank Dr. Selvaduray to be our technical advisor, as well as Ms. Label and Dr. Simako for providing support in our project. So here's the references we have. And thank you so much for all you guys listening. So any questions, concerns?
How long typically does it take one of these wounds to heal? Like we give a regular staple. About
After applying, approximately it took around 1 to 2 weeks for normal metal stable to remove, but it generally takes approximately a month to entirely healing for the healing process.
So it's about 15 days or 14 to 17 days for a wound to start, get
kind of forming, yeah.
Form. So does that kind of affect your choice of absorbable staple at all? Like as far as how far they've absorbed by that point?
So yeah, that's a really great point. So because we are using the PLGA as a main material, it's because the FDA already approved some device using the PLGA, just like the one we mentioned is the absorbable stable. So in order to, we do admit that maybe the biodegradable stable may need a longer time for it to completely dissolve. But we want to consider the FDA consideration too, because if we're using other materials as the main materials to close the wound, so we have more process to follow up to the FDA. So we want to using the PLGA, which PLGA already approved some device using that material, so we try to follow it. Yeah.
Now, do you know if the staples would have to be sterilized before they're used, and if that would have any impact on the polymer?
For the staples, right? Yeah, I think for the stable, they usually, the entire stable will be sterilized and then put in a package. So I don't think we have a chance to actually manually put in the stable. in a cell. So I don't think for the sterilization problem will not be a huge problem for this.
All right, let's stop there. Thank you. You'll make it. You'll make it.